Well, what are we speaking about today and tomorrow? We are speaking about application of optical fiber systems in the network. You have learned everything about component, which means mainly fibers, amplifiers, but also passive components. You have learned the important parameters you have to take into account for designing an optical fiber system. Now we are going to see where and how optical fiber systems are used in the network. Today, and maybe a couple of hours tomorrow morning, we will deal with all the network, telecommunication network, save the first mile, the access network, which will be dealt with tomorrow. Well, let's start. This is the overview of the presentation today, which means we will start with general aspects of optical system application. Afterwards, we will go to intra-office systems, which are those systems mainly devoted to interconnect equipment inside a central office or between two central offices very close. Then we have metro access networks, metro core networks, backbone networks, and submarine system. At the end, we will give just an overview of the new trend in optical networking, which is WSON, that is to say, wavelength switched optical networks. In the history of optical telecommunication, we have seen many different phases. At the end, the fiber was only used to replace copper, with, of course, much better performance. When I was young, the most high bit rate system was, the higher high bit rate systems was 140 megabit per second over coaxial cable. The distance between repeater at that time for such systems was 1.5 kilometers. Afterwards, the fibers arrived, and the distance was increased to some tens of kilometers, 20 kilometers, 30 kilometers. But it was only a simple replacement. Afterwards, the span increased up to 100 or 150 kilometers, but it was still a replacement. After, at mid-90s, the optical amplifiers became commercially available, and we were able to send many different optical channels at different wavelength by means of WDM over a single fiber, but it was still point-to-point link. You have seen from Mr. Makoto some very special components, add and drop multiplexer or photonics cross-connect, which are able to switch a single wavelength inside a comb of many wavelengths, 16, 40, 18 wavelengths. You can take one of them or more, of course, out of the comb. You can send to a different place, and you can replace that wavelength with the same wavelength, but carrying other signals. This is switching. So with the advent of optical add-and-drop multiplex, we are able to switch lambdas, to switch wavelengths. Well, wavelength-switched optical networks are the trend towards an optical network which will be dynamically switched. That means that the network alone, without any human intervention, will be able to switch wavelength whenever a fault occurs or whenever the traffic load is changed. That means that with no operator intervention, a light path, which means a lambda which is going from CTA to CTB to CTC to CTC, will be switched from A to Z to C because of the fault in the link. But we will see it at the end of the presentation. General aspects. This is a list, almost complete, of ITU recommendations dealing with the characteristics of optical systems. The colors group them by argument. You can see that recommendations are mainly concerned with the interfaces. The definition of an interface is very important if you want to connect systems between them. I was saying that we are using wavelength, but of course the wavelength should be the same. It's like having a TV transmission. You have a comb of frequencies which is arriving from the terrestrial antenna or is arriving from the satellite, but you must have a TV receiver which is able to receive and detect those frequencies, not other frequencies. The same applies to optical system. If you transmit a comb of, let's say, 40 wavelengths, you must have a receiver which is able to receive and detect those 40 wavelengths. This is interface. Of course, it is not only a matter of wavelength, it is also a matter of power level. You cannot increase the power level, otherwise you will blind your receiver. But you cannot have a very low power level, otherwise the bit error rate will increase to very high value. But we shall see. The recommendation in green, 691, 6941 and 6942, are devoted to the definition of the reference value for the wavelength combs. Just like in television, you have a channel which are exactly at those frequencies. Here, in this recommendation, we define grids of optical wavelengths where you can allocate wavelengths. You cannot use other wavelengths. Otherwise, the system will not be able to detect the light. At the end, we have multi-channel WDM. You already know what is a WDM system, but we will have another look later. These are other recommendations dealing with optical transport network. This is a very important concept. An optical transport network is a network where anything is only optical. You don't have any access at the electrical level. The electrical level is at the starting, at the ending of the network, but not inside the optical transport network. Optical transport network is a network connecting large group of users which are spread over a large geographical area which can coincide with a nation, with a country. So the optical transport network can eventually cover all the country. Depending on the covered area, the optical transport network has been subdivided into 4 different sub-areas. The access network, which is the network where the users, the customers, be they individuals like us, which are staying at home and want to phone or want to browse the internet, or enterprises needing more higher bandwidth for business, for delivering content, for accessing contents at a very high bit rate. This is access network. The access network is collected by the so-called metropolitan access network, which is the part of the network normally inside a large city, connecting a few access networks between them and to the other region, which is the metropolitan core network, which is a regional network covering an entire region. We will see that from a geographical point of view, these networks will be defined by the average length of the links. We will have very short links for access, medium links for metropolitan access network, links around 100 kilometers for the regional network, and the long-haul network, which is the network connecting all the country as a backbone, or the country with other countries or continents, which means links more than 1,000 kilometers. All these networks benefit now from optical technologies. In my country, in Italy, sometimes I read the paper and I see that some journalists write that the government or the Ministry of Communication has decided to put fibers in Italy. We are putting fibers in Italy since 1980, only fibers since 1980. So all the networks are optical. The last part of the network, the access network, the legacy network, which was used to connect the home telephone to the network, I mean the copper wire, the copper pair, are still used, but have been improved to transmit XDL up to rates of 10 megabit per second and so on. But now the trend is to replace also the copper wire with fiber, so that eventually, in 10 years, 15 years, or maybe 20 years, all the network will be optical on optical fibers. It's only a matter of investment, of course. The required investments are huge, mainly because of civil works, because, as you know, the optical fiber cost is not higher than the copper pair, but possibly is lower. This is a schematic picture of an optical transport network. The optical transport network is the one in the gray oval, and you can recognize some acronyms that should be familiar to you from the previous days. We have optical line terminals, OLT, which are the standard terminals in central offices used to connect users. Then we have optical amplifiers, OA. We have optical add and drop multiplexer, which you know are devices able to extract, which means drop, or to add, which means replace, one or more wavelengths in the wavelength comb which is going through the optical add and drop multiplex. If I can reconfigure such a device, the OADM will become a ROADM, R-O-A-D-M, where R stays for reconfigurable. You can choose on a dynamic basis which wavelength to extract. You can choose both the number of wavelengths to extract and which one. By the way, my USB stick pen is going around the table for downloading the file with the presentation. I don't know where is it now, but it's circulating. This optical transport network can accommodate many client signals. What's the meaning of client signals? Well, we started from an electrical world. We are still in an electrical world. My computers, your laptops, in this moment are connected to a wireless hotspot, and this is electrical. It's a special kind of electrical. It's radio, but it is considered electrical. It is not optical. Well, we started from electrical networks, which means PDH, SDH, ATM, Ethernet, flat relay, and so on. Well, we cannot throw all those networks away. We made a lot of investments, and the SDH network is still there and is working perfectly. So, all the networks are to be transformed in a dynamic wave. The approach is the evolutionary approach. If you think about the PDH network, the first one to have a high bit rate, when SDH arrived, the PDH network was still there. Which was the evolution? The evolution was to replace links in the PDH networks, which means I am going from central office A to central office B, which is 200 kilometers apart. Well, I will not pass anymore in the PDH network, but from central office A, I will go in the SDH network. I will transmit the signal. I will exit the SDH network going into the central office B. So that I am replacing links in the old PDH network with transit inside the SDH. Well, now we are doing exactly the same thing. I have an electrical SDH link between central office A and central office B, and I have an optical transport network below, which is acting as a server network. I cut the link in the SDH network. I send central office A to the optical transport network. I transport the signal, I exit the optical transport network, and I go inside the central office B. I am replacing one time more links. And in the same time, I can say that the SDH signal is a client signal of the OTN network. At the end, all the links in the SDH network will be replaced, and the SDH network has gone forever. In that sense, I listened to Makoto yesterday, or maybe the day before yesterday, speaking about legacy system. A legacy system is a system which is still operating, which we accommodate inside the optical network as a client, and which is going to be replaced as soon as possible. Please, of course, you can interrupt me anytime you like. You can ask questions, and if I am able to reply, I will reply, and the normal way. Please.
Thank you. In page 7, we have subdivided areas which are covered by the fibers, of which we have metropolitan access. It is on page 7.
Page 7 of what? The end book?
Slide number 7. Yes. So of those, I have question on metropolitan networks, because we have 2 of them. I understand for metropolitan network, the recommendation which applies is G.652, and for long overhaul is G.655. So my question is, does G.652 apply for both access network and regional? And the regional, the one you said core networks is regional.
Well, this is a good question. It is a question that is asked every time. And I would like to address this question at the end of the 2 presentations, which means both today and the access network today, because we have several types of fibers, and people ask every time which fiber is most suited to a certain application. I elaborated a table which is at the end of the presentation tomorrow, and we can discuss it in details. But for the time being, what I can say is that the G652 fibers, of course in the modern version, which means type D or type C, is applicable everywhere. And it depends on the kind of systems you install if you are going to choose different fibers, for example, the G655. You know that the main parameters which are related to the fiber choice are the attenuation, the chromatic dispersion, and due to the high number of channels traveling along the fibers, to the nonlinear effects, which are related to the power traveling along the fiber. You know that if you have 1 milliwatt of optical power, this is not too much, and you will not experience any will not experience any problem due to nonlinear effect. But if you start with 40 channels or 80 channels, as they are installing now, the 1 milliwatt will become 80 milliwatt or 40 milliwatt, which is a few megawatt per square meter inside the fiber. If you don't have any objection, I think that we can deal with your question. I prepared the table with all the application and which fiber is most treatable to which application, including access networks. If you don't have any problem, we could address and discuss it later tomorrow at the end of the presentation, because this is the question. Okay? Which are the most important parameters or aspects to be considered in an optical transport network? Well, the optical transport network must be able to provide us with some important functionalities. The first one, of course, is the transport. I should be able to transport signals, packets, or data, or other kinds of signal from point A to point B. Multiplexing. Multiplexing is always a means to reduce cost. In this case, multiplexing means to send several channels on the same fiber through WDM systems. Routing. Routing means to be able to switch inside the optical networks, to route inside the optical networks the signals. This is mainly done at lambda level, which means in optical transport network I am able to switch a single wavelength. Some vendors are selling systems which are able to perform switching at sub-lambda levels, which means 1 lambda can be used to accommodate different signals, and in some vendors' equipment you may switch these signals individually. This matter is not addressed by ITU recommendations, so that we will not deal with it because it's linked to the single vendors, for the time being at least. Management. Management simply means to be able to control the switching. Means to be able to control the performance of the network. This is a very important aspect because as I told you before, when a client signal, let's say an SDH signal, enters into an optical transport network, you will not have access to it until it exits the network. So, if you are familiar, or for those of you which are familiar with the SDH frame, you know that there is a huge overhead in the SDH frame, which is to be used to monitor the performance of the SDH. By examination of some bytes in the overhead, you can understand what is the error probability. You can understand if there is any fault somewhere. But when the SDH frame enters the OTN, it is no more accessible. So you are not able anymore to perform bit error rate monitoring. To this purpose, OTN provide different monitoring means by supervisory optical channels, which means that one optical channel is added to the comb and is used to monitor the performance of the network. So that, as in the SDH, you can understand if a given regenerator is in a fault state because the error probability before that regenerator is good, it's 10 to the minus 12. After is 10 to the minus 6, so you can understand that the regenerator is in a fault state. Here, you should have the possibility to monitor optical amplifier, for example. In the network, you have a lot of optical amplifiers, but how can you know if the optical amplifier is working properly? The optical amplifier was installed to give a gain of 25 dBs. But when the gain goes down to 18 or 16, you should monitor it. All this information are put in a collateral channel, optical channel, which is used for supervision. The other important aspect is the survivability of optical channels, which means that if there is a break in a fiber somewhere, or if an optical amplifiers or optical added drop multiplex fails, you should be able to recover from the fault with both either human intervention or automatic intervention. All these aspects are given in the listed recommendation. Yes.
You just said that within the optical, I can say, platform, there is the supervisory in the management, the supervisory channel. And this supervisory channel is attached onto the comp. Yeah, to the comp. So I just want you to expound more about the comp. And what is the spelling of that word you have just spoken? Yeah.
A collection of wavelengths, which are the comb, of course, it's a collection of wavelengths which resembles a comb. So you have a lot of wavelengths which are spaced, for example, 100 gigahertz apart, and are used to transmit signal. You have 40 of this wavelength. On one end, not very close, far from the signal transporting wavelengths, there is another wavelength which is used to transport monitoring supervisory information signals. So it's, maybe I can use the whiteboard here. These are the wavelengths. This is the main comb, 6 wavelengths that transport signal. Here you have the supervisory channel, which is far apart, so that it can be easily separated from the signal transporting wavelength, can be reduced to electrical level, and can be requested to provide information. Since for the time being, we are not able to process signals at optical level. We are not able to store information at optical level. We are not able to retrieve information. We don't have optical computers. We have only electrical computers. So that if I want to add information to the supervisory channel, I have to detect it, to extract the electrical information, to read, to modify, and to modulate again the laser to retransmit the optical supervisory channel. And it is far apart from the other channels in order to be splitted from them, to be separated very easily with low-cost components. Well, this is a diagram showing how a client signal is accommodated inside the optical transport network. The client signal are those on top of the diagram. There are some of them, of course, not all the electrical signal we have available nowadays. We have IP packets, which are sent with the MPLS protocol. We can have ATM cells, also if, even though ATM is a declining technology, nobody is going to install it as a new installation. Then we have Ethernet, or the new generation of SDH. At the right end, we have those systems that we call legacy, which are the old systems that we should accommodate to save investments. As long as the SDH, the old SDH network is still working, we will retain it because it's money. These are, for example, first generation SDH systems at STM-N and gigabit Ethernet. All these signals are accommodated inside a single wavelength, which is called optical channel. So the optical channel is a lambda, a wavelength, carrying one type of signal. The optical channels are joined together to form the optical multiplex section. The optical multiplex section is the part of the network in which we have several different lambdas, the channels of the WDM system, traveling together in a bonded way along just one fiber. The optical transmission section is the fiber, is the part of the network in which we have what I call the comb traveling along the network. Normally it includes fibers and optical amplifiers. The blue part of the diagram is the optical supervisory channel, where I add information pertaining to all the clients together. The blue part carries information about all the signals which are going inside the multiplex. Optical channel construction is detailed inside the recommendation G7009, and we start from the electrical signal which is put inside an optical channel. The procedure is very complicated, it's a complex procedure, but we shall see later. The optical channel, as you can see from the colored part of the figure, is just one wavelength. In this case is the orange wavelength. For the other two wavelengths, the red and the blue one, we have the similar construction. We have the client signal which is sent inside an optical channel. It is to be noted that WDM is a multi-service network, which means that on the orange channel I can transport SDH, on the blue channel I can transport gigabit Ethernet, on the red channel I can transport ATM. I can transport heterogeneous traffic on the same fiber through the same amplifier, which is a very powerful unification means. It means simply that you start from different networks, which in some cases were really different. They had no intersection point. Now you send all these networks inside the optical transport network using different lambdas. The optical channels are multiplexed together in an optical multiplexer, a WDM multiplexer. You saw it during the component session. And the result is an arrow of colors, each wavelength carrying a signal. After exiting the multiplexer, the optical multiplexer, the total signal made up different lambdas, by different lambdas, is transported just one link, along just one link, a single link, fibers plus amplifiers. The construction of the optical channel, I will not insist on it because it's out of the scope of this tutorial, but I want to transfer to you the main concept. The main concept is that we are going to add to the original signal some overhead which needed to get the required performance. It is not yet shown, but part of this overhead is given by the addition of an FEC, which means a forward error correcting code. If we apply this procedure to a familiar signal, for example, the 10 gigabit per second SDH signal, it is really 9.488 gigabit per second. All those overheads which are added to the signal are extra bytes added to the frame to incorporate monitoring overhead. At the end, the final electrical signal will have a bit error rate which increases to 10 point something. Sorry, I don't remember the exact number, but it's more than 10, which means that we have added extra bytes, including the FEC. You know that the FEC was used at the beginning only for submarine systems or satellite systems, and it is able to correct errors up to a given limit. But from an external point of view, it simply means that instead of having a very high bit error rate, let's say very low bit error rate, let's say 10 to the minus 12, you can have links in which the bit error rate goes up to 10 to the minus 6, is increased 1 million of times. But by using the FEC correction characteristic, the equivalent bit error rate is still 10 to the minus 12. This is very important. Please. At transport level, which is the very low layer in the layering of ISO-OSI model, there is no retransmission of signals. So if the bit error rate increases to 10 to minus 3, it has gone forever. If you are watching your favorite match on the television, you will see the boxes, and it has gone forever. Retransmission is foreseen only at the higher level of the ISO stack, which means that Ethernet packets are retransmitted if they arrive corrupted, but are retransmitted in another frame, hoping that the bit error rate now will be a good one. But at transport level, there is no retransmission at all. Yes, but as you know, you have 7 layers in the ISO stack. Your browser is at the 7th level, and optical transport network is neither level 1, is level 0. It has been added as a blind transport level. When your browser is not satisfied with the packets arriving, it will ask for retransmission, but it applies at 7th level. At 0 level, no retransmission at all. It's impossible because you are going 10 and eventually 40 or 100 gigabit per second. How can you have time to retransmit something? You have a return signal saying, please transmit again the frame. It's impossible. So no retransmission at all. However, it's a good question. It gave me the possibility to fully explain what is level 0. Well, you start with a link that should have a 10 to the minus 12. Then you add an FEC in order to be able to tolerate a degradation which is 1,000,000. You go from 10 to the minus 12 to 10 to the minus 6. If the FEC is not able to recover the signal, it simply means that you have a very bad link. What to do? Change the link. So, well, I'm sorry because I speak in a very familiar, colloquial way, but I think it's a good way to fully explain what I mean, besides the theoretical aspects. But this can be done automatically. Take the example of the SDH. In the SDH, normally you have the same frame is transmitted along two different, in a ring, is transmitted in one direction and in the other direction. The receiver listens to the frames and select the frame with the lower bit rate. It means that if you have a direction which is better than the other, you will select that direction and you will get the frame from that direction. If I cut the fiber immediately, where immediately simply means 50 milliseconds, immediately the receiver will switch to the other direction. If you are speaking to your mother or your girlfriend, you will not understand that something went wrong. You continue speaking because 50 milliseconds is a very low period of time. So there is no problem. What is the problem? The problem is that you are transmitting 2 times the same thing. And this is money, of course, because you are using twice the bandwidth which is required. In optical transport network, the approach is a little bit different. We are not applying 1+1 protection, which means the signal is not transmitted along 2 different routes, but if something goes wrong, the light path is diverted to another path. At least in the head, in the brain. Actually, commercial systems are not able to perform this automatic switching, but it is on the way. I am an expert of the European Community, and I help the Commission to assess the projects that are financed in the field of optical communication. Last week I was in Barcelona, Spain, to assess a project, a small one, which is named DICONET, whose main task is to develop automatic switching procedure in case of failure. And I saw a demo acting on 3 real networks nodes in which the switching was done in less than 1 second. Let's say 800 milliseconds. 800 milliseconds is much more than 50, but we are on the way. And we are lucky because this switching happens very rarely in the network because faults are not very common. And I saw the demo on a real network, which is the Deutsche Telekom network. I incorporated 1 slide from DICONET, we will see it later. And it's a very complex network with 46 degrees, which means there are 46 links connecting all the major cities in Germany. And the traffic from Berlin to Munich was diverted through Hanover in the time I mentioned just before. The name of the OTM, which is Optical Transport Module, is classified according to a couple of numbers, where the first one, the N, simply means the number of channels which are transmitted. So N could be 4, 8, 16, 32, 40, 80, and so on, while M means which kind of a client, let's say, which kind of a client bit rate is transported. It can go from 2.5 gigabit per second up to 40 gigabit per second for the time being, but works are on the way to transport also 100 gigabit per second Ethernet. Well, now we have just introduced the optical transport network. We are going through our complete network from a geographical point of view, and we start with the general picture, highlighting the sub-area in which the optical transport network can be subdivided. We have at the very left the blocks representing the customers, which can be single customers, a home, can be multi-dwelling units, apartments inside the buildings, can be enterprises, from small offices up to large enterprises. They gain access to the network through the access network. All the data which are collected through the access network go inside the metro access network, since most of data and telephone traffic is consumed in a very small region. What I mean is that normally when I make use of the telephone, we will take as an example the fixed line telephone, I phone to relatives or I phone to colleagues, but mainly they are located close to me. I am living in Rome, I am all my relatives in Rome, so that whenever I phone them, the telephone call will not go outside Rome. This is the region for the introduction of metro access. Most of data will be confined to the metro access. All the metro access areas, the green one, are for the exit traffic, are going inside the metro core, which has an extension of, let's say, 100 kilometers in diameter, and from the metro core, the traffic is sent to the long-haul optical network, which means extra-country, sometimes extra-continent traffic. When I connect to Microsoft to seek for help on a Microsoft application, and I already know that the help will be of no help, my data go to Seattle. So from Rome, they have to traverse Europe, and after they have to traverse Atlantic Ocean. This is the long-haul network. It can be 1,000 kilometers. Which topologies are used inside the various parts of the networks? Well, for the backbone, which is the country level network, all the major nodes are connected, usually by point-to-point WDM links in a mesh topology. It is not that the mesh is complete, no need for having each node connected to all the other nodes, but normally a mesh is used. In metro networks, both access and core, the favorite topology is the ring topology, on which we normally have still WDM system. For the access network, the preferred topology is the point-to-point or better point-to-point, in which, as we will see tomorrow, the cost of the infrastructure is shared by many users. You have one equipment in the central office, and this equipment is able to service 5,000 users. So the cost of the equipment is divided by 5,000. This is a list of the most important ITUT recommendations dealing with topologies. And as you can see, there are some recommendations related to point-to-point, others related to the so-called bus structure with add and drop multiplexing functions. And the last two, the series G983.x, which means .1, .2, .3, and so on, and the G904 covers point-to-multipoint topology for optical access network, we shall address tomorrow. This is the most simple link. It is the point-to-point link. I told you already the concept. I will repeat since it is very important. In such a topology, we have